So what is it then that we get if we find that the parameters n times p exceed or are equal to 10 and n times 1 minus p exceed or are equal to 10? What do we get? Do you remember that discussion? No?
That we get that it's normally distributed
That's right. It's going to be the case that not that it's normally. I didn't go that far, but I said that
approximately normally.
no, I said that it would be symmetric, remember? I said that it would be symmetric, and then um with this condition, so if p is equal to 0.5, you're going to get symmetry. But further, if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, it's going to look symmetric and approximately normally distributed. So yeah, I did say approximately normally distributed. But the idea was I was pushing the idea of symmetry, which you would get if p is equal to 0.5, but this is even stronger. Symmetric and approximately normally distributed. What does normally distributed imply? How would you say what's normally distributed if somebody asked? You would say that the observations or the values, if it's a distribution, the values are spread out symmetrically such that 95% of the observations are within 2 standard deviations, 99.7% of the observations are within 3. There are 68% of the observations within 1 standard deviation, like all those features of the normal that we know, and even more detail. Those are just 3 features. The idea that there are 0.3% outliers, right? Those are the features, but also all of the other information that we can drive with more detail from the standard normal table and further from Excel, right? So we have all that detailed information about the distribution that we can now use in place of making this calculation. So I'm going to do a couple of problems like that. Not couple, I'm just going to show you that. Then what I do next in module 8 is create a new, what do I call this? What is this? What is X? What do I start to call X? X is a variable, but if it's a number derived from what I'm calling a sample, what is X?
The successes.
Yeah, but it has a name that starts with S, not successes, but another name.
Was it the sample name?
No, we're not there yet. No.
Oh, okay.
So we are remember, we're going to treat this like it's a sample. So I can say n trials or n draws. This is like a sample, and X is a number I compute from the sample. So in essence, what is S? X. What is X? What's a number computed from a
Statistic?
sample? Say it again.
A statistic.
A statistic. Okay, so X is a statistic. And SDS stands for sampling distribution of a statistic. And the statistic is X in this case. Okay, so X is treated like a statistic. And as a statistic, X has okay, as a statistics, we talk about its distribution. So there's the distribution of a variable, then I make it more specific talking about the distribution of a statistic. And in a distribution of statistic, a distribution has a mean and standard deviation, right? So here's the mean of the statistic X, and here it's standard deviation. And I actually go through and derive these. Now, you don't have to derive them. You just have to understand those. So this is the mean and this is the standard deviation. So buy it for now, but if you didn't see that or you missed that, go back and watch the video. I explain that or look at the notes. So this is the mean of X and this is the standard deviation. Now, for any N and P, X will be the statistic with a mean NP and a standard deviation NP. But in certain cases, that is where N times P is greater than or equal to 10 and N times 1 minus P are greater than or equal to 10. This will be the mean, and this will be the standard deviation of that normal distribution. Okay, so that's a lot of information there. This is really an outline for the remaining of the course. So you get familiar with this, right? So for example, see if I can, I have to get out of here. Give me a second. Hold on, I want to see the chat. Right, Juliet wrote number of successes or statistic. Okay, let me get the. I'm just getting module 8 on my iPad. Okay, so this is an example here where P is 0.5 and N is 20. It's like the minimum case, or it's where we will have N times P is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. You can verify that. And it will give a shape that is approximately normal. Now remember, the binomial distribution is a discrete distribution, so you only have these spikes here. Why we call it an approximation is because we impose the idea of a normal distribution, a curve around them. And to do that, we put these bars around each spike of 0.5 on either side. All right, so as I mentioned last class, the distribution is binomial the distribution is symmetric if P is equal to 0.5 or this is true. And further, it's going to be normal if this is true. So I apply that here. I present here an example. Let's say X is 100 draws or 100 trials where the probability of a success is 1/3. Find the probability that X is greater than 23. So that would mean that X is X can be from 0 to 100 successes, but you're interested in greater than or equal to 23. So you would have to calculate for X equals 24, X equals 25, all the way to X equals 100 and sum them. And as I mentioned last class, that seemed unnecessary for statisticians who are aware of this relationship to the normal. So rather than do this without a calculator or Excel, they would use the approximation. They would calculate the mean as n times p, calculate the standard deviation as n times 1 minus p. Both of them are greater than 10. So they've shown that X is approximately normal with mean NP, standard deviation NP1 minus p. Take a moment and make sure you can verify those calculations. You're going to get, you're going to have a lot of calculations like this. So it's important to be able to make this calculation. I'm going to use this number below as well. Okay, so verify that you can get that. The theory rests in checking. So this is the checking step, step 1. I am on page 18. Okay, so you got it? So now what do we do with that? Now we're going to take the question, X greater than 23, and we're going to convert it X to a normal distribution. The n times p that we calculated was 33. That's the mean. So I use the symbol. Let me make it a little bigger. I use the symbol, the mean of X. Okay, so this is, you don't have to write all, like, just as long as you understand. I'm just trying to emphasize this is the new mean or the mean of the variable X, which is a normal now. So that's the mean of 33, which you can compute. And the standard deviation is NP1 minus P. All right, so it's not exactly N1 minus P, it's NP1 minus P. And that's the variance, and you have to take the square root of that. So make sure you can make this calculation, okay? Confirm you can get this number. It's a little bit tricky, especially with the fractions. And you need to keep the fractions there because you might lose decimal places. Remember, I asked you to be careful with the fractions and retain them. Let me know if you get 4.71. I'm just calculating this. So 100 divided by 3 times 2 divided by 3. That's how I see that. And the square root is 4.71. Does anyone need to see that again? Did you get it? Got it? All right. You guys are very quiet. What's going on? You don't have much time. You have to work on this class. And I'm here right now, so take advantage. Aprovechan. Okay, so what do I do now? Now I solve the question as though it's a normal. I standardize X, I standardize 23. How do I standardize X? I minus the mean and divide by the standard deviation. If you don't like the symbols, just write it in words. So X minus the mean, divide by standard deviation, standardize it. That's what you do here. And you end up with this Z greater than negative 2.1. So I draw negative 2.1 over here, 2.19. And I want this area. How do I get it? So now you have to go back to your tools from the normal distribution, which I told you couldn't forget. From the table, you can only get the left side, but you take that from 1 to find this area. And the answer is 98.57%. So that's very interesting, right? Greater than 23 is almost, well, 99%. Okay, so what is this saying? What is this saying? This is saying that if this is true, that the chance of a success is 1/3, and you try 100 times to look or observe, in a sample, the chance of getting more than 23 successes is extremely high. Almost 100%. It's like 99%. So I'm talking about the results of a sample, right? That's basically what I'm doing here. Now, in reality, but we'll talk about reality in a moment. Okay, so if I knew the chance of a success is 1/3 on each try, then out of the total 100, 20 more than 23 successes is 99%. So that's very interesting. All right, so that's just one example.
Can you say that again, Professor, please?
What I said is we're going to try 100 times to look for a success. The chance of a success is 33.33% or 1/3. Then in our sample of 100 tries, the chance that more than 23 are observed is almost 100%. It's 99%. Which at first glance, you wouldn't know that. You wouldn't understand how 1/3 plays out in 100 draws. Okay, but in this binomial phenomena, the chance of getting 23 successes, 24 or more successes is 99%. This is an approximation. I use the symbol to denote approximation. And then later I talk about trying to do this precisely. To be precise, we have to account for the fact that we have to adjust for the density that we've added around the spikes. Let me jump to that before I continue. So I talk about that over out here. I think I used the same example. Okay, so all of this looks really intimidating, but it's not a big deal. Okay, I'm going to show you an example. The same exercise we did. If we want to find the exact value, not an approximation, we have to make an adjustment. So here's the original problem. And this is just repeating what we just discussed. We do the check to make sure that it's greater than 10 in each case. Then we have the mean and standard deviation, n times p and p1 minus p square root. We calculate them. So 1 and 2 we've already done. Now what? What I want to find, so what I'm thinking is, this is 23. This is 24. And what I want to do is account for this density adjustment. Continuity correction, it's called. So I want to include 24. So it says greater than 23. It means exclude 23 and its bar, but really it's going to be 24 and more. Do you agree? So how am I going to write that? So I have these different considerations here. If it's greater than 23, I have to start not at 23, I have to start here. What would this number be? What did I tell you about the area, adding the area? Where would I be right here? At 23.5. So the continuity correction factor is either adding or subtracting 0.5 to account for this bar around the 23 and the bar around the 24. So rather than solving the problem x greater than 23, I convert that, make a continuity correction, and I call it continuity correction factor is x greater than or equal to 23.5. And that's what I solve. So I repeat the same problem, same steps, but I make that 23.5 instead of greater than 23. All right, and that will account for and give me an exact value. Now, I'm not going to put this on the test, but it's pretty simple. And it's important if you go on to use or apply statistics to know what a continuity correction factor is. Okay, so statisticians have these kinds of adjustments and approximations, and it's just important to know how they fudge things, okay, how they fiddle with numbers to make them work. So you'll see when you solve this that, so these two steps we just did, so you can review those, but making the correction that I just wrote, now you standardize that and you get slightly different number. It's a little bit smaller. So, but this is known as the exact value. It's a little bit smaller because we got rid of that, little bit of area. So this is And it's not, like I said, sometimes we add 0.5, sometimes we subtract 0.5. Okay. And that's gonna have different effects if you're going left or right. So I wouldn't bother memorizing all that. I just draw the picture and I know how to make the adjustment. So you're gonna compare this with what we had before. What was the number before? Let's go back. It was a long time before. 98.57. Okay, so you compare that with 98.57, it's a little bit smaller. This is known as the exact, not the approximation. This is the exact. So you might see some problems that say find the exact, and sometimes it'll say find the approximation. If it says the exact, you have to do this little step before. Would you like to do another one? Do you want to see, you want me to slow down? You can just do another one to reinforce. No? No comments? Okay. There's some practice assignments here. So here I say here. So here I ask you to use, I'm very explicit, use the continuity correction factor. So that's kind of the thing. But you'll see in some exercises I might refer to the exact value. Okay, let's have a little talk about what if it's at a value. Remember, when we say with a binomial that we want to find the probability at a particular of a particular number of successes, we do have an answer. But if it's in a continuous distribution, this would be 0. Remember that discussion? So how we deal with this in making the adjustment to make it more meaningful using those that density that we added around each spike, we have to add a little bit on each side. So let me show you what I mean. Let's see if I have an example. I think I'm just going to have to do that 23. So let's say the question here was, because I guess we'll just go here. What if the question was find x equals 23 using the continuity correction factor. So you would have are you seeing what I'm seeing here? So I want 23. In other words, I just want the bar 23. So what is the adjustment? How do I prepare the question with the continuity correction factor? I have to go here and here. In other words, 22.5 between, the x is between 22.5 and 23.5. And I make that an equals now. I can use it equals. It doesn't matter though if I'm in the normal. It doesn't matter. The equals or not equals or less than, the symbols all matter. Equals or not equals is important for the binomial, but not so much for the normal. But I wrote it like that here, so I'm going to stick with it. So then you standardize and solve this as you would the normal. Any questions about what I'm doing here? Questions? Are you following me? So basically this, I want 23 using the normal. I have to adjust it. Otherwise, what would be the answer? Using the normal, it would be 0. We don't want 0. We know there's density there. So that in the approximation is just 0. But with the proper continuity correction, it should have a value, right? So we add density around and we solve it. Do you need me to do the rest? So this is going to be then P, you're going to take 22.5 minus the mean, which was, I'm using 33.33. And then this becomes a Z, divide by the standard deviation 4.71. And then 23.5 minus 33.33 divided by 4.71. And then you do the between. Okay, so finish that off yourselves. I don't have an answer there, but the point is it's not 0. Okay, it has some density. So that's the continuity correction factor. Again, I'm not going to have that on the exam, but it's important that you understand anomalies like this situation. And that's how I'm approaching it. So if you see something like this, that's how you deal with it. Okay, so remember that. That's at 45 minutes in this, or maybe 40 minutes in the video, if you want to see it again. Okay, so the next thing we have to talk about is, I have a lot of examples in here. It's not, they're very repetitive, but make sure you study all these exercises. Most important thing. All right, so what I want to show you is this discussion here. No, going the wrong way. Okay, so here I make all the proofs. You don't have to repeat this. It's just proving using the rules we learned in module 6 and 7 about rules of means and variances to derive all these results. Okay, I would derive all the results we're using that are on the formula sheet. I introduce the idea here. P hat. What's P hat? If anyone's read ahead or understands, what's P hat? So P hat comes from X. X is the number of successes in N independent trials. If I divide it by the total number of trials, I get what's called the sample proportion. So for instance, we were talking about 23 out of 100. So X equals 23. it's the same as 23%. So the answers should be the same, understanding the possibility of an outcome x greater than 23 or x greater than 23%. We should be able to get the same answer. It's really just two ways to say the same thing. 23 out of 100 is the same as 23%. Does everybody agree? And mostly we talk about percentages. So we use the basis. We started with the binomial. We made it a normal. But really, we don't talk about counting all the time. Like there are people who deal with the counts, but when you hear news reports or results of studies, they always talk about percent. So we have to make this extra step. Divide by n and get the percentage. Now, how does that affect the theory? Not too much. First, I need to remind you that if x is a statistic, also p hat is a statistic. Okay, so x was the count. As a statistic, p hat is an estimate of what? P hat estimates p. This is the true population proportion. I'm on page 19. The population parameter. So p hat estimates the population. It's very important from here on out that you understand the difference because that is going to mess you up. Okay, so p hat is the statistic. It's the population. It's the sample proportion. Even use the words rather than the symbol at the beginning so you get the hang of it. This is from the sample, and it's intended to estimate their true proportion. Now, right now, you're going to see that I use them both at the same time, and I'll explain why we do that. But this is where we start. Okay, everybody with me? So p hat is the sample proportion. What is its mean and standard deviation as a distribution? Oh, it's very messy here. Okay, so let's see. Let me go to, let's see if I can erase this. All right, so let's read. Given x is binomial NP and provided that this approximation applies, right? The approximation we talked about, then p hat is the proportion of successes, not number or count, the proportion of successes, which by the above is known to have approximately normal distribution. Okay, so I'm going to use, just to distinguish it, I'm going to use the symbol, the mean of p hat and the standard deviation of p hat. But don't freak out. That's just for you to know this is the mean of this one and standard deviation of this one. Now, how do we find this and this? These are my answers of what the mean is and what the standard deviation is. Where do I get these numbers from? Well, let's start with x. Go back to x. We knew that x was normal with a mean of NP and a standard deviation NP1 minus P. We were just talking about for the last hour. I get these results from, and it's in the notes, I derive them from the rules of means and variances that we learned earlier. All right. And then what I'm going to do, if I can divide x by n to get p hat, can I just divide the mean by n and the standard deviation by n? Well, the rules of means and variances said, yes, they told us that. So part of what we learned when we talked about that, but don't worry if you don't get it immediately. So all I'm going to do is take this one, divide it by n, and this one and divide it by n. And what do I get? These cancel and make n a p. And to make these cancel, I have to right. Does everybody agree with that? I have to put the n inside of the root. Is everybody okay with that? I put it in there? Because to take it out, I have to take the square root, so it becomes n. So to put it in, I have to do that. And then it cancels. And I get this result here. So these look they look familiar. You're going to have to rewrite them several times, so get used to them. Because in fact, we use p hat more than we use x. Okay, we use p hat more than x. The mean of p is p. Somebody explain that to me. The mean of p hat is p. Someone explain that to me. And the standard deviation of phi hat is p1 minus p over n square root. The mean of p hat is p. What does it mean? So let's say we do this, we do our sampling, or we look for our successes out of n trials. We run, in other words, we run the trial, right? We sample. And we get so we can talk about the example again. X is binomial. N was 100. And P was 1/3. Remember, the same example. So let's say we did that and we got the sample. We found, let's say we got 23 out of 100. So that is 23%. Okay? Let's say we did it again. And let's say we found 50 successes out of 100. That's 50%. Let's say we did it again. And we got 65, or let's make it a small number. I'm just making this up. So let's say we got 35 out of 100. That's 35%. And we could do this again and again in all possible samples, right? What it's saying is that the average of all, so if I took all these values and I average them, what would I get? What does the theory tell me? Which is what, Juliet? This is my example here. We're always back to the same one.
So you get the true proportion.
Which
of
is what?
all
Which is what in this example?
P,
Which-
P without the hats.
Yeah, but what is it in this
Uh,
example?
1/3.
Exactly. That's what I want you to connect. Okay, so this is going to be the P that you start with. This is my P. So that's what the theory is saying. If I did this repeatedly, and I don't have to do that, right? Because I usually take one sample. I don't repeat and repeat. But statisticians did that. Okay, statisticians ran these empirical studies to verify that this happens, and they're able to do it in the computers at any time. You know, they can create a randomization and test their theory. But the theory says, if you were to repeatedly sample, on average, if I average all of these, the average would be the true mean. Now, it's going to be different on any one try, but on average, the long run relative frequency would be 1/3. Is everybody okay with that? So that's what's going on here. So as I promised you, you're going to use p hat more than, you're going to talk about the proportion more, you're going to talk about the number of successes. Okay, so you're not going to talk so much about the number of people who will vote Republican in the upcoming election. But you're going to talk about the proportion of people. They don't usually talk about the number because then you have to ask a secondary question. How many people did you did you sample, or how many people does this represent? So by presenting the proportion, it kind of covers everything. It tells you the percentage of people of whatever number was sampled or whatever number was observed. Okay, so you kind of get this. Some of you don't get it at all, but I use the same example all the way throughout. Review it. But let's see what it all means, okay? So I'm going to go back to my formula sheet and summarize. Let me go back to the formula sheet and summarize. So in summary, we learned, let's start from the top, that X has a binomial distribution with parameters N and P. Then X has a mean of NP and standard deviation of NP1 minus P, which is in the notes. And I tell you, those are from using the rules of means and variances. You can calculate the probability exactly by applying this formula for each case. But when it gets unruly and your N is huge, you want to use the approximation. When N is population size is large, you want to use this normal distribution, where the normal distribution would have a mean of N times P and a standard deviation N times 1 minus P. Sorry, what am I doing? Sorry, the distribution that's normal with a mean of NP and a standard deviation N minus P, and you can only do that when these conditions are met. Okay, so this is a little different than that. Don't mix them up, which I just led you to almost do. Okay, so next, we learn about X over N, which is the proportion, the sample proportion. So you can put that down to remember that's what that is. That's a sample proportion. If this is the sample proportion, we're going to call this the sample count, a counting variable. Note that the sample proportion is continuous. Okay. Also, we like continuous variables, so that's another reason why people use this instead. And the sample count is discrete. Remember that difference. And this also applies under the same conditions that we talked about NP greater than 10 and N1 minus P greater than 10. And we can answer similar questions given information on N and P. I can ask you questions about what to expect in a sample outcome. The mean of the distribution for P hat is P, and its standard deviation is P1 minus P over N. And this comes from taking these and dividing by N. And we understand the interpretation is that the average of all possible samples will give us the true proportion. So this is from the binomial topic. This is from SDS, sampling distribution of a statistic. And also this is from SDS, number 3. What this says is regarding X bar. If X has a mean of mu and a standard deviation of sigma, the sampling distribution of X bar, so let me just specify. So what we did here was deal with the bin of X. What we did here okay, so right here is where I talk about the sampling distribution of X. Here I talk about the sampling distribution of P hat. And so in number 1, it's the sampling distribution of X. In number 2, it's the sampling distribution of P hat. In number 3 is the sampling distribution of X bar. And I have a video there in Moodle to just describe what is going on here and where this comes from. And I'll explain it. Let me do a little explaining here. if you're told that, here, hold on, let me clean up a bit. Let me give me a line here. So if you are told about a variable x that has a mean of mu and a standard deviation of sigma, what would you expect in a sample drawn from that distribution? What would you expect to see? That's what we're talking about here. So, for instance, if you get your blood pressure measured, and now they actually have machines that do this automatically. If you've had an opportunity to get your blood pressure measured on one of these machines, you'll know that any individual blood pressure reading is not a good representation of the blood pressure. That could be because people are nervous. They're in a strange place. Someone's taking their blood pressure that they don't know. And or they're nervous. They're actually somewhere checking because they're not well and they want to know what their blood pressure. And there could be in a doctor's office, just on a routine checkup. But usually if you are in worried and you're in a hospital or someone's checking your blood pressure because something has happened, or even in a routine visit where you're worried about your health, you will be nervous and your blood pressure will be high or higher than normal. Okay. So the first reading is not the most accurate reading or representative reading. So as you're sitting there, this machine will take time and take your blood pressure several times, not just once. Okay, individual readings can be very volatile if you compare them over a period of time. But if you take 3 readings over a shorter period of time, or 5 readings, and you average them, they would be more representative. Has anybody had that experience before with their blood pressure or been with a parent or a loved one that they take the blood pressure more than once? One blood pressure reading isn't exactly representative. So, what I've just described is here. Any sample from this distribution, so you can think of this as a distribution of your blood pressure readings over a long period of time where your health is relatively stable or whatever. It's not exactly, even if you're sick, let's say, or ill where your blood pressure would be high, that it's not so volatile around the mean. So you have some certain mean, whether it's high or low, and you have your certain standard deviation. And if you were to draw from that population, any individual reading would not be as accurate as if you took a sample. So if I took a sample from there, the mean should be the same. Okay, so a sample of several readings from the population should be the same on average. So if I did it just like I explained the thing about drawing. Okay, so if I was to draw from this population here, and I got a mean, right? So I got X bar. So let's make some numbers. Let's say this was like 175. And this was 5, or or 15. I have an example of that in the notes too. I'm just making up these numbers. So let's say it was 175 for a particular person and 15 was the standard deviation. And on the first try, you got 170. And then on the second try, second sample, you got 165. And on the third one, you had 180. Okay, so you could do this over several, this is just repeated sampling. Okay, so I sampled here. So I got a bunch of, so this could be on one, visit. Let's say we took 3 readings when we talk about the blood pressure. And then on this visit, we took 3 readings. Okay, so 3 readings, 3 readings. And I calculate the sample one day and another day, and this is another day or another part of the day. What would be the average of those? All the repeated samples. What do we expect the average to be? So these are the sample means. If I repeatedly sampled, now that might not necessarily be the case. I'm talking about the theory, right? So if we repeatedly sample from that distribution, what would be the average of those averages, in other words? So this ... means all possible samples. What do we expect? Anybody? Anybody awake? Anybody thinking here? Just take a guess. Juliet. Very good. Very good. It's not the sample mean, it's the true mean. Okay, so on average of all possible samples, we should get 175. That's what this says. Okay, so if you have a distribution of a variable x, the sampling distribution of x, so what I've created here is a sampling distribution by repeatedly sampling. The average of all of these should be the true one. If I do consider all possible samples. Okay, so we've discussed that. Now, where does this come from? How can you interpret this? The standard deviation. So the average of all of the averages, or the mean of all the averages, sample means that you took, should be the true mean. But what about the standard deviation? Going back to the blood pressure example, I expect that the standard deviation of these samples to be smaller. In the blood pressure reading, I told you that if you take a sample and you calculate the mean, that's better than any individual reading. That is captured here. This is a smaller number. This will always be a smaller number because n is positive, the sample size. So this is smaller than that. Okay, that's what this says. Now, it's obviously, there's a pattern here. It depends. It's smaller, yet the larger your sample size. So the more times you take that blood pressure reading on each individual draw in all possible samples, the standard deviation of all of them will be smaller, be tighter. In other words, they're going to be closer to the true mean. This is why this is why budgets or scientific experiments or surveys, they would love to have unlimited funds to sample a lot, right? Because why? Because the larger the n, the smaller the variation around the true mean. It means that your sample result will be more meaningful and more accurate or close to the true value. Okay, so there's a lot in this. So it's going to be smaller, and it'll be even smaller the larger the sample size. So in so many words, it's going to be smaller than if on any individual draw. Okay. This is the basis. What we were learning here are the basis of sampling. large sizes for samples and surveys and experiments. But we're always restricted by cost, right? Our budgets. We can't do that many. We can't do an unlimited sampling, but we do prefer larger sizes if we can afford it. So there's some examples that I give. Let's just do a couple. Let's just do one because we don't have too much time. I want to get into this stuff down here. All right. Now this will all make more sense if you go through the videos and the notes on your own. I'm doing an overview, remember. So this will be repeated. All right, so let's look at some examples together here. The simplest examples are these ones. Okay, let's do this third one here. Okay, let's take a break. Let's take a 5-minute break. You guys can read this, get a snack, make a call, and I'll be back here at 10:17 or 18. Okay, let's take a break. But we're going to try these examples on page 36. I'm going to pause the recording. Okay, I'm back. All right. Okay, so let's see what we can do here. How many of you got this far? How many got this far in the review? Okay, all right. So a company produces a supersized bag of chips advertised to contain 454 grams of chips. In reality, the weight X, so that's the variable, of the chips in each bag is distributed normally with mean 460 grams and standard deviation 10 grams. Okay, so now this is asking us to consider so we're going to apply this. All right, now they talked about X being normally distributed. That's going to be in the brackets here. So X is given to you as normally distributed. Notice it doesn't have to be normally distributed. Okay, so, but if X is normally distributed, then these results apply. If X is not normally distributed, these results apply in approximation, provided you have a large enough sample size. All right, so this result here, whatever, everything that's written in 3 here, tells about the shape. This tells about the parameters. So the beginning here is talking about the parameters. If you begin with the distribution's mean and standard deviation, you know the mean of the sample mean will also so the sampling distribution of the sample mean will have the same mean but a smaller standard deviation. Now this bracket is talking about the shape. Also, X bar will be normally distributed provided X, the original variable that was given, is normally distributed to begin with. And if it's not normally distributed to begin with, as long as your sample size is large enough, it will still be normally distributed. Okay, what the heck am I talking about? So first, these parametric results apply for any distribution. In the brackets here are just talking about the shape of the distribution. All right, so let's see, what am I talking about? So you're told here that about a normally distributed measure for the weight of a bag of chips produced or manufactured. Okay, so you're told that you begin with a variable x that is normally distributed with a mean of 460 and a standard deviation of 10. Then you take a sample. That's what it says here. So consider the sample mean with a random sample of 25 supersized bags. Then the sample mean, so this is like the sample of 25 bags comes from a distribution that is also normal with the same mean, but a standard deviation that's smaller. So you have to calculate it. You take the original 10 and you divide it by the square root of the sample size. What do you get? Right, 2. Okay, now what do we do with this? So what did we answer? We answered the question, let x bar denote the sample mean calculated from a simple random sample of 25 bags of chips. What is the distribution? So we can imagine taking one sample, but that one sample we take, what we expect it to be in terms of its parameters, or sorry, its mean and standard deviation, we expect it to come from a distribution of sample means, and that is going to have this shape, this mean, and this standard deviation. Okay, now let's apply it. So I've answered all the question, the distribution, and I've answered this distribution and its parameters. I didn't ask exactly explicitly for them, but that's what it is. Okay, if you draw a simple random sample of 25 supersized bags of chips, what is the probability that the mean weight of the 25 bags is between 4, 5, 8? So we're going to write the question that x is between 4, 5, 8 and 4, 6, 5. And I'm going to use the x bar. Sorry, I forgot that. I'm using x bar because it says this, mean weight. Okay, so this is a little bit different than what we were doing before with the with the normal distribution. I'm working with the mean weight. X is the weight of 1. X bar is the mean weight of 25. Let me write this a little clearer. Okay, so what do we do next? What's your instinct? What do we do next?
We would have to get the C-scores, right?
Standardize, right? Yes, standardize. Yeah, so go ahead and do it. Put your answer in the chat. Very good. Amaris. Standardize, get the z-scores, but you're doing it with X bar now. And because of this, it says mean weight. If it said weight, you would use this one, X. Did Amaris get it right? Yep. So I did 465 minus 460 divided by 2, and that's going to be 2.5. Right. Very good. So you have to use your talent for the normal distribution to solve these problems. Z less than -1. Right, so you look those up. 1587 for -1, 0.9938 for 2.5, and take the big one minus the small one. And you get. Any questions about that? Can you do that? So everything falls up from this result. So this is the new material, right? This is the sampling distribution of the statistic X bar. So the rest is familiar. Preguntas, dudas. Ready for the next one? We're going to do C. ¿Listos? Okay. Okay, let's see. You need 4.5 kilograms or 4,500 grams of chips for your guests. You buy 10 supersized bags, hoping that this will be enough. What is the probability that that these 10 bags hold enough chips? So we're going to assume that selecting 10 bags off the shelf is essentially the same as selecting a simple random sample of size 10. If Okay, so we're using the idea that it's a sample of 10. So just like I derived the results for X and P hat using the rules of mean and variances, similarly, these results draw from applying the rules of means and variances to a normal distribution X, okay? And right now we have a sample size. We're talking about a sample size of 10. So we have to repeat what we did in part A, but for 10, N of 10. So given X so given X is normal, it's the same result there. Then with a sample size of 10, X bar is also normal with a mean of what? It tells us here that the mean of X bar should be mu, the original one, but the standard deviation smaller by a factor of n. So the mean is still 460. The shape is the same, but the standard deviation is sigma over root n, which is 10 divided by square root of 10, which is what? Right. 3.16. So for these problems, you can keep 2 to 4 decimal places. For probabilities, I always tell you to keep 4 decimal places. Here you can keep 2 to 3. It kind of depends on the numbers themselves, how big they are, but if it's a decimal number, keep 4 decimal places. All right. Just to make sure your numbers are the same as mine mostly. So you can follow. Okay, so now we set it up. This is for the mean, but they're asking us about the total weight of the chips in 10 bags should exceed this amount. All right, so we want to check, but let's be clear. This is the weight of 1. This is the mean weight of 10, but they're asking for the total weight. Now, how will I deal with that total weight? Do I have information on the total weight? I have information of the weight of 1, the mean weight of 10. How do I deal with that total weight? Can I do it like I did it above? Can I answer the question as above? We have to convert the statement here to the mean weight so we can apply this, all right? Otherwise, we can't do this problem this way. The options are we divide this number by 10 to get the mean weight and apply this, or create a new distribution that represents 10 bags and multiply both of these by 10. But that's not what we're going to do. We're going to do it this way, okay? So you take the statement of the total weight and divide the total by 10. Okay. Now answer this question. So what you're going to find is the probability X bar exceeds 450. So you had to make that transformation of the question to be able to answer the original question. Follow me? The question wasn't exactly using what we have here, mean weight. So I had to divide it to turn it from total weight into mean weight. And now I can answer the question. Standardize with the mean of 460. Oh, sorry, I'll just do Z. So now this becomes a Z, 450 minus 460 divided by 3.16, because 450 is below the mean, right? What do you get for the Z score? Or Z score? Anybody? First, give me the Z score. Negative 3.16, that's right. It's over here, right? It's far away. So if you look up 3.16 in your table, you get the left side. What's the probability? What's the probability there? So this is 0.0008, Juliet? Yeah. So then we have to take 1 minus. It's a high probability, right? 9992. Okay. So if the mean is 460 with a standard deviation of 3.16, the probability that it's going to be more than 450 is pretty good. It's almost 100%. All right. Okay, so the exercise here is to know the difference between the original variable and the sampling distribution of the sample mean. All right, so this is the result of repeatedly sampling creates a distribution with this mean the same, but a standard deviation that's a factor dividing by the sample size. So it's smaller. It went from 10 to 3.16. And it would be even smaller if the sample size was higher. All right, so there's problems like this. And then there's also theoretical problems. Okay, imagining. Just remember the difference between the original values and the sampled values. The sample means it's a different variable that's related. That's the point. Okay, the next thing I'm going to do is just one more. I know it's getting close to 11, and I do want to introduce inference, but this is the foundation of inference. So you got to have some sort of understanding of this. What I'm going to do next is the next problem where we do not necessarily know the distribution of the original variable, okay? Here I told you it's normal, so this one's normal. But if it's not normal, another result known as the central limit theorem is that it doesn't matter as long as the sample size is big enough, we have this result in approximation. So I'm going to write that, well, I guess I'll write it out here. So this is the problem. Read the problem. We'll discuss it. Okay, how many people in a car? A study of rush hour traffic in San Francisco counts the number of people in each car entering a freeway at a suburban interchange. Suppose that this count has a mean of 1.5 and a standard deviation of 0.75. In the population of all cars that enter at this interchange during rush hours, could the exact distribution of the count be normal? Why or why not? What do you think? What do you think? Who thinks it's normal? Who thinks it's not normal? Say no or yes in the chat. I can see some of you, but I can't see everyone. Exactly, Aleximar. Damaris. Yes, excellent. Okay, so you got the idea, right? I hope. This is a practical question. It's very important to know that what's happening in traffic for city planners, construction, the government, they want to know how things are moving. The exact distribution of the count cannot be normal because it's a count variable. It's a discrete variable. So that's important. So the answer to that is no. But I've already shown you in a few instances where I can. So when we were talking about a binomial counting variable, we could get the normal in certain circumstances. And also in this theory that I'm going to present, or that I've already presented, but I want to specify the case where you do not begin with a normal distribution, you can have the sampling distribution as normal. So it works like this. This is known as the central limit theorem. And it says that if you start with a variable and you know its mean and standard deviation, but you don't necessarily know the shape, as long as n is greater than or equal to 25, the sampling distribution of the sample mean will be approximately normal with the same mean and a standard deviation that's a factor, small, making it smaller. It's a matter of what the sample size is. Okay, so that's known as the central limit theorem. You don't necessarily know the distribution, and that's the case here with the rush hour traffic. Or even if you knew it and it wasn't normal, it would be fine, okay? So the point is that it's not necessarily normal. It's called the central limit theorem. This is very important because we're going to use this results. All these results we're learning today are going to be used for inference. Okay, so points 1, 2, and 3 on that formula sheet are used for inference. This theory is relied upon to be able to take sample results to say something about the population. All right, that's basically it. These are the sample results or findings, and I want to be able to take that result that I get from a sample and go back to guess in an educated way, infer what are the parameters of a distribution. So that's what we're going to do next. But in the meantime, let's finish this. So traffic engineers estimate that the capacity of the interchange is 700 cars per hour. According to the central limit theorem, what is the approximate distribution of the mean number of persons x bar in 700 randomly selected cars at the interchange? Can you guys do this without me? So 700 is more than 25, so this applies, the central limit applies, and you can get this result here. What's the mean and what's the standard deviation? Tell me. So going back to the problem above, the mean was here, the standard deviation was here. Those are the numbers you're going to use. So this is 1.5, and the standard deviation will be 0.75 divided by 700. Which is what? So when you're in the decimals, I said, hold 4 decimal places. Oh, I forgot the square root, right? Careful. Ugh. Not good. 0.75 divided by 700 square root equals. Okay, can you guys get me a number? I'll show you my calculation too, just in case you're having trouble with the calculator. Point 0.75 divided by 700 square root equals. Very good. Very good. Very good. So just, yeah, keep 4 decimal places. Some places, maybe in the textbook, maybe some exercises. I don't simplify the numbers, but I feel like it's important to simplify them here until you understand what I'm doing. So I'm just going to use 4 decimal places. It seems easier to punch this all in piece by piece in the beginning. All right, 2802834. That's too many. So I'll just do 0283. I don't want the numbers to get out of control. All right, so that's it. So now we're going to use this distribution. Remember, it's a mean. So this is the average number of people in a car in a sample of 700. This is the central limit theorem. So as I said, you might know the shape, but it's not normal. So it's not known to be normal. I just put it, doesn't matter what it is, as long as the sample size is more than 25. Okay, so now let's apply it. What is the probability that more than 700 cars will carry more than, what does I say? That's not what it said. What is the probability that 700 cars will carry more than 1,075 people? So I make a hint, and this is similar to the one we just did with the bags of chips. Restate this event in terms of the mean number of people in a car. So this statement here, I'll just write it out. Is that right? So the problem will be solved using this, which is the mean number of people in a car. This is the total number of people in a car. This is the mean number of people. in a car looking at 700 cars. Okay, out of 700 cars. That's what it is. So answer the question now. Using this here. What do you get? That's right. So I want to standardize. Be careful when you do the math. I'll show you again. So I'm going to take 1.54 minus 1.5 equals, and then divide by 0.0283 to get 1.41. Did anybody else get a different number? Very good, Eliximar. I'm gonna make it big and do that again. So you just finish the problem. You want to go greater than 1.41, you have to go in this direction. So again, it's 1 minus, or the alternative is to change the sign in the direction and you get the same answer, right? Get used to that because you need to learn about the t distribution. So if I change the sign and the direction, I get the same answer because of symmetry. So you can look up negative 1.41 to get the answer without the 1 minus. The tables always show you to the left. So 1.41. 1.41 negative is 0.0793. Very good. Very good, Damaris. Okay. So it is a small chance that there will be more than 1,075 people in 700 cars. It's a very small chance. Given the parameters at the beginning, that's the result. Okay. Any questions? So I just reviewed from the formula sheet 1, 2, and 3. 1 is about a count variable, the number of successes and n trials, or the number of things you're looking for in a sample of n, right? Number 2 is about the proportion of successes in a sample, or the thing you're looking for in a sample of n. And 3 is about the sample mean. So different problems, we'll talk about proportions or counts, or for these, to know that you're doing this kind of a problem, you're talking about problems where you're given a measure or something like that. In this case, we use the central limit theorem, so we actually did start with a count variable. Practice will help you distinguish between what you have to do, all right? And the better you get, the more practice, the better you see these patterns of how you're supposed to approach these problems. So you have the practice assignments, you have the homework, you have all those things to practice, rehearse this. What I want to do next is introduce inference. So inference, so you guys have all that to look at. But we're going to start here. Now I'm going to finish this row, okay? If you have to go, just go. It's fine. I'm going to finish this row. I'm going to put it online. You guys can start at around 2 hours in and follow my discussion here. You'll see it repeated in the video's instruction. You don't have to watch this. I just feel it's imperative for me to get through this in the review classes. Because once I do this, the rest pretty much falls out. I'm going to cover this first row and I'll stay no more than 12 o'clock. I don't think it's going to take me. Okay, so we're going to go into module 9. To do this. Let me stop share a moment. Okay, let's start here on page 5. That's where I want to take you. Okay, so this is page 5. Are you ready? I'll give you a minute. In a study with a new vaccine involving 53 lung cancer patients, 29 survived 5 years after surgery. The approximate 98% confidence interval for the true proportion of patients surviving 5 years after surgery with the new vaccine has these endpoints. Okay, it's okay if you didn't understand any of that, all right? What we're going to do here is focus on proportion. Okay, we're going to begin with proportion. That's number 4 on the formula sheet. And these are the results of an experiment. What was the sample size in this experiment? What was the N? Damaris? Anybody else? What's the sample size? Okay, you see that? Okay, so, all right, so this is the sample size. I agree. 53 is equal to N. How many people survived? What do we call 29? 29 is a number of people survive. What symbol do I give 29? Survival. Is that a success? 29? What symbol should I give this success? The thing I'm looking for when I run an experimental study. What symbol? Not K. What symbol should it be? What's a success? What's the label we give to counting successes?
Is it hat?
Not there yet. Not there yet. You're close. The number, not the proportion of successes, but the number of successes. We're almost there, Laura. You're right. But first I need to know what 29 is. X is the number of successes, right? X is a number of successes and 53 trials is 29. And now, Laura, we are going to calculate P hat. P hat is X over N. Very good. 29 over 53. So what do we get? What's P hat? Very good. You just divide them. 0 point and into 4 decimal places, it is 3 decimal places, it is 0.547. And I told you to keep 4. That'll put a 1 on there, right? But in the options, they're all possible now because they're all showing p hat as 0.547. So we have that. So let me talk a little bit more. So you guys are able, that was the part you could do. All right. Now where are we heading next? We found the sample size. We have the number of successes. We found the proportion. And what we're going to do, this represents the sample result. 54% or 55% of people survived after surgery with this new vaccine. Okay. Obviously, there's more background story, but this is a simplification. Okay. Now, I want to present this in a publication. I want to make a report. I want to talk to my supervisors. Okay, this is how many people survived in this experiment. We want to try to generalize it to all possible experiments of this type. So we use the theory that we just developed to do that. We imagine that this could have been repeated. We make some assumptions about this being this being drawn from a large enough sample, a large enough population, and we use the results from number 2 that say that P hat has without knowing anything. Notice I don't know anything. I just gave you 3 lines here and the results of an experiment. I don't know. Maybe we've never done this before and we have these results. So we don't know the behavior of this population, but we're counting on the central limit theorem to help us. What we're going to say is that P hat approximately normal with a mean of P and a standard deviation. Do you remember P1 minus P over N square root? We want to use this result. But do we have P in the 3 lines I've given you? Is P there? The true survival rate? Is it anywhere there? Who sees it? Or you don't see it. If it's not there, just say, no, it's not there. No. If you think it's there, give me the number. You see P? Can we find it? We are in the topic of inference now, where P is unknown. P unknown. What do we do when P is unknown? Because everything we've done till now, I give you the parameters, but now I'm going to take them away. I'm going to take them away. But I'm going to count on the theory still. So I'm going to take the idea of the theory that says, if I have information on X that's binomial N and P, I'm just going to write this here and I'll move it after. Then, and it satisfies the requirement NP greater than or equal to 10 and 1 minus P greater than or equal. I'm just copying out from the theory, okay? Then in approximation, P hat is approximately normal P square root P 1 minus P over N. So what we're going to do, this is really oversimplifying, but what we're going to do, I'm going to erase it here. Is say, what are we going to do if P is unknown? What we're going to do is draw a sample. And from this sample, we're going to use the idea that this is one result from a distribution that is normal with a mean of the true proportion and a standard deviation calculated like this. So that means I want to create not just this result, this is just one sample result, but I'm going to build what I call a 98% confidence interval. In other words, I'm going to show an interval where 98% of the observations are captured. If it's normal, if this is a normal distribution, what would be, how many standard deviations would I be from the left and right to have 98% in the middle if this is normal? And so let's use the standard normal. Where would I be here and here to have 98% in the middle? So you got to go, it's 98 in the middle, it's 1% here and 1% here. So where would this be here? That doesn't look right. So let's go look at the table with 1% on the left. We'll do that here. Okay, so I have to go inside to look for 1%, right? So that is 1% is like here, right? Okay, smaller, smaller, smaller. Okay, so between here and here. Very good. 1% is on the left of negative 2.33. We'll go to the closest one. Oh, Eliximar went. Oh, okay, so we could also, yes, I'll talk about that in a second, about the t-table. So this is negative 2.33. We can be more precise, and I'll show you how to do that in a moment. First, I'm going to write that down here. So this is 2.33, and that's just to 2 decimal places. Everybody following so far? So I found the position. So if you're within 2.33 standard deviations of the mean, you will get 98% of the observations. So what I want to do, what happened? I hit something. Turn off. Oh no, what's happening? My iPad's doing things I don't know what it's doing. It is, oh, I hit maybe this? No. Okay, we'll just leave it like that. Ah, stressful. All right, so what I want to do is take this number 0.547 and I want to go 2.33 standard deviations from the mean. So I want to put here the standard deviation. So that's the way I'm going to create an interval, right? So I'm going to use 2.33 and standard deviation, and this is like my mean, right? I'm going to use this as the center, or what I'm going to call the point estimate. So this is the point estimate from my sample. And then I'm going to do plus or minus. I'm going to use a z-score that gives me, in this case, 98% in the middle, but I can change that. But I'm going to call it a z-score. I'm going to put a star in it because it's a special z-score that corresponds to how much I want to capture of observations from the center or around a point estimate. And then I'm going to multiply by the standard deviation, or this, I'm going to call it the standard error. That's a special word that I'm going to explain. All right. That is similar. I've written it in different terminology, but it's just a what we've been doing, where we say we take a, like, recall, where I take the mean and I plus and minus 1 or 2 or 3 standard deviations. Oh, sorry, I should use when we were doing this, plus or minus a standard deviation, plus or minus 1, 2 standard deviations, right? When I was teaching you how, or I taught you how to interpret mean and standard deviation. Well, now we're going to do it here, but using the point estimate plus or minus a particular number of standard deviation. It doesn't have to be 1, 2, or 3. It can be to create a certain percentage of observations in the middle. It doesn't have to be 68, 95, and 99.7. It could be anything. There's just some standard ones we use. Often we use 95% for doing that, sometimes 99%. But you should be able to do it for any by getting the number of standard deviations from the mean from here. This is all possible because of this theory we built, okay, that we're working with the normal distribution. How do I find the standard deviation? I'm going to go to the theory here as well. all I'm going to do, so what I basically did was I substituted, because I don't know P, I'm going to substitute the P hat for the P. That's what I did here. I made it like the mean, the center of this interval I'm going to create. And then I'll do the same thing with the standard deviation. I'm going to put P hat inside of here. So the standard deviation is computed using P hat, 1 minus P hat over N square root. Now, because I'm not using P, I'm using an estimate, we call this not the standard deviation, but we call it the standard error. It's a special word to refer to calculating the standard deviation with an estimate inside of it, okay? So it's an estimate inside of our estimate. So we call it standard error instead. Same idea though, same pattern. So can you guys do that for me? Calculate the standard deviation. So you have to take 547 times 1 minus it, which would be 453 divided by N, which was 53. Don't forget that number, and take the square root. So get that number for me. And then we are pretty much done this problem. Sorry. Go ahead. I'm alive. I just dropped the calculator. What do you get? Okay, so let's see. So like I said, if you have to go ahead, and I'll just continue. I'm gonna finish this row and make sure you watch this before next class. The fourth row. So let's punch it in together. .547 times 0.453 divided by 53 equals square root, and that's right. So 0.0684 would be the value. Very good. Some of you did it. It's important to practice and not just stare at what I do, because the main thing is don't forget the square root. The other thing is the 1 minus part. You need to get that correct. And because they're multiplied, it's easy to divide, right? And then equals, make sure you get the equal sign before you take the square root. So those minor things you're going to notice just with practice. All right, so you ended up getting I'll erase this stuff here. .0684. So now you can see your answer should be 0.547 plus or minus 2.33 times 0.0684, and the star here is to multiply in the options. So the closest one would be B. But why do they have 4 decimal places? Our table only gives us 2 decimal places. So now I'm going to show you where this number comes from. So first, before I do that, can you guys all confirm you understood what we did here? So I am using this theory without knowing P, but I'm counting on it, where I'm going to take my one sample, rely on the fact of the theory that it comes from a normal distribution of possible proportions, of all possible proportions. I just got one, so it still should be able to represent the distribution of them. I'm going to use it at the center and put an interval around it. Now, there is a catch to that, and I'll talk about that in a bit. Actually, I'll talk about it next class, exactly what the catch is. But we are just going to practice using this technique. And then I go back to understanding what I know about the normal distribution and being so many standard deviations away. I want to capture 98% in what's called a 98% confidence interval. And I use this calculation, the substitution of p hat instead of p, to get what I call the standard error, but it's like the standard deviation. It's just that I used an estimate in there because that's all I could do. So this is much more practical. In fact, why would we even have statistics if we knew all the parameters in the first place? But we don't know the parameters, and that's why we developed the area of statistics. And all of this stuff about inference is a whole theory behind protecting us or defending us in using estimates to infer what parameters are. Okay. So we don't just get one result, we get an interval of results because of the unknowing, because we don't know for sure. We present an interval of results. Okay, so where does this number come from? This 3, 2, 6. I give you another table. So this is the t distribution. And in your review this week, you should learn about it. On the bottom of this, okay, let me just show you the whole table. So this is the t distribution, the t table. And it looks like the z distribution, right? It looks like the standard normal. It has 0 in the middle. Depending, however, on the sample size you have, this changes. The higher the sample size, the more peak this is. Okay, lower sample size is more flat. In other words, the tails are thicker. And that gives you more probability in the tails or extreme values, more likelihood of extreme values, in other words. So you'll see the sample size is captured here. Do you remember what these degrees of freedom are? Do you remember our discussion or my explanation of degrees of freedom in the videos? What's degrees of freedom? Degrees of freedom are n minus 1. Okay, so if you need at least 2 observations, and then your degrees of freedom will be 1, and you're going to use this row for the table. As the sample size gets bigger, the degrees of freedom get bigger, and I explain this in the videos, this whole table in the videos, but for now, I just want to use the last row because, as I said, as the degrees of freedom get bigger, you have a larger sample size. The t distribution looks like the z. That's what the z star is. So it just looks like these are actually the z distribution. And in fact, you can find the confidence level and how many standard deviations from the mean you will capture that percentage of observations. Okay, that's what confidence interval refers to. So our number here, 98%, is what we wanted. We have to be precisely 2.326 standard deviations from the center mean to find 98%. So that's why I use that value. The more popular one, often you'll see in reports and research and news reports too, 95% is used. And the critical values, we call that critical values or Z stars, are 1.96. So that's what this is called. This is called the critical, I'll refer to it as a critical value. Now there's more to this table, but that's all we're going to use right now. So we took this one here. All right, let's go back. And that's it. So, but we could do it without the T table, right? The T table on the bottom row of the T table, it will give you 3 decimal places. It simplifies things a bit, but I need you to know where this comes from because the T table doesn't have all of them. Okay, it just has a few. Know how to get rid of this. Anyway. Okay, so I'm going to take this statement here, and rather than say Z star, I'm going to refer to this as the critical value. I'm going back to the formula sheet. I'm going to leave you with the formula. Oh, I want to use the one on the other in the other file. Okay, so here we have the first item on row 4. This is known as a C% confidence interval. It's one of the things you got to calculate, or you are responsible for in inference. So this is inference. This topic here is inference on a proportion, population proportion, but P unknown. We don't know P. Otherwise, why would we try and guess P if we know P? We don't know P, but I have to stress that. So this is called the point estimate. This is called the critical value. And this is called the standard error. Okay, and I've shown you where to get the critical values from and the point estimate and somewhat about using the theory that we developed previously to be able to argue that this is a good representation of the proportion, right? This is a, so you're going to present this as the proportion, or the proportion of survivors. And it's not going to be just 55%. It could be a range of values. If we go back, and I do a bunch of examples, applying that. But let's just look here. What's your chance of survival? You have to actually multiply these and then add and subtract it. Can you make the interval for me? And put it in the chat. So multiply these and add and subtract from 55% here. Do it, well, just whatever. Do it to 3 decimal places because that's what's there, but give me the upper and lower bounds. That's what we're going to do with this. Yeah, I'm going to stop at 12. So if I don't finish all 3, it's okay. I will stop at 12. As long as I get through at least one of these. So you're going to multiply 2.326 times 0.0684 equals, and now you're going to add and subtract 0.159 from 0.547. So that this, what I've multiplied, do you guys know the name of this? This has a name too. You might have heard it before. It's called margin of error. Yes, the margin of error. It's the plus or minus. It's the margin of error. So your margin of error is 0.159. So survival is on a range of 39% and 71%. So what we found is an estimate of the survival rate from this experiment between 39% survival and 71% survival. Okay. Got it? Do those look like good odds for you or good estimates? I guess if you have a really serious condition and there's nothing else, it looks pretty much better than 0. So you have to measure that against the, well, this is 5-year survival, so it's pretty good. Okay. Let me put that on the formula sheet. I'm going to call that margin of error. I need it. What am I going to do with the margin of error? Okay, any questions? You guys have been pretty quiet. But you're still here, so I think you're following. All right, so that we've basically, this is the first row of inference, and notice there's sort of a pattern here where I'm doing the same thing. These are all confidence intervals. This is for inference on the population proportion where P is unknown. This one is in inference on a population mean where sigma is known, and this is inference on a population mean, sigma not known. Okay, that's what we're going to talk about next week, but hopefully you're going to get there on your own and see the pattern. There's a pattern there where I'm always going to multiply, I'm going to add and subtract the critical value multiplied to the standard error. So this is the critical value, and this is called the standard error. So these things look familiar, right? Because this is from 3, and this is similar. We'll talk about that. When we don't know sigma, we substitute it. What's the best substitute for sigma? It's the sample standard deviation. But by using that substitution, we lose the ability to use the z standard normal distribution for the variable. Instead, we use t star. And so you'll see an explanation about the t distribution and all that. Okay, so don't worry, this will be coming, but I just wanted to point out there's a pattern here. Okay, so column has been introduced. The next column is very interesting. This is known as sample size estimation. I spent some time talking today about sample size, noticing that the higher the sample size, the more precise your estimate can be. Or the more, like when we were looking at the blood pressure readings, right? I said if you take more blood pressure readings from sample to sample to sample, reading it on different days or different points of the day, they're going to be closer together. They're not going to be so volatile, right? If you take a larger sample size. But what's the right sample size? This is another question. What is the right sample size? How large should it be? Well, that depends. If this is going to be our interval estimate, look at what it depends on. What does it depend on? What are the things you can control as a researcher? If this is going to be your interval estimate, what can you control here? What does the researcher get to pick? So if you want the interval to be tight, notice the n is on the bottom. So the larger the n, what happens? The smaller the interval. Is a small interval good? It means it's more precise, right? It means that if you get a really broad interval to estimate something, that's not very reliable. If you get a very tight interval, it's much more reliable. So if somebody went and spent millions of dollars to estimate something, like let's say even in our experiment, and the standard deviation ended up being really high, it would be meaningless. Like if we go back to our example of the surgery, our interval is above 0, right? So that's good. I mean, what would make it smaller is if this was a smaller number. So what if this was 0.0068? It would be much smaller. That would be even better. But what if it was big? What if it was 0.6? Then this would spread out so far that you're saying, oh, well, it could be between 0 and 100%. So who cares? Like, that's not really information. If someone said your survival rate is between 0 and 100%, you already knew that. So it's useless. You want it to be tight. Okay. You want it to be tight. So we can control the n, but the question that we're heading for is, what should the n be? What is it going to depend on, and what is it going to depend on? Well, it's going to depend on the z star, and it's going to depend on the p as well. So these are the variables: the p hat, the z star, and the n. The ones we can control are the z star and the n. The p is kind of given to us, right? From either the sample, or somebody gave it to us in advance because it was determined on previous or older studies. But sometimes we won't even have the p. And what can we do? So these are all the variables that control or affect the confidence interval, or our estimate. Uh-oh, that's not what I wanted to do. All right. So what we're going to do instead is we're going to take what's called the margin of error, right? We're going to take this. And what I'm going to do with this is call it M. And I'm going to say, let's say I want a specific margin of error. I want a specific number. What is the sample size I need? Do you see now we have an equation? So if you fix this, if you want to control the margin of error, you have to also establish what is your confidence level you want, and you have to know something about P, either from a previous study, or I'm going to show you what to do if you don't have any information. Then you can find n. So let's solve this equation given m. So I'm going to put check marks what we know. So if we know m, we know what our z star is, and we have some idea of p. Solve for n. Can you do that, algebra? Oh dear. This is not behaving the way I want. All right, so all I'm going to say to you is solve this for n. Okay. I'm going to change p star, sorry, p hat to just be p star because I might not have a sample result. Okay, so I'm going to call that p star. So I'm going to do that right here. So this is going to be m equals z star. And I'm going to call this p star, like whatever p I have, I'm going to put it there over n. And then so algebraically, I have to do this. And then that leaves me with this. And hopefully you can see that I need to square both sides. Okay, are you guys doing it? Are you watching me? Okay, so that's what I did so far. Convince yourself that that's correct. Right. And the last step is to cross multiply. You're going to flip that fraction and you're going to move this whole thing here. Cross multiply. So n is equal to, I have to flip this. And multiply p star 1 minus p star. And that is a formula for sample size estimation. And I have to put the star back on here. And at the time I started teaching, there used to be commercials for Mazda.
Professor,
Yeah.
I think the P star goes in the coefficient, right? It's you need to switch. Oh no, you're right. You're right.
All right.
Continue. Yeah.
It's okay. I was considering what you were saying. So yeah, you get to use these formulas, but it's nice to be able to be familiar with them. Okay. And I would refer to this, not to forget the square. I would tell my students that this is the zoom formula. I don't know if you remember those Mazda commercials, but they used to talk about zoom. So this is a square term, okay? This comes squared, and that's from unsquaring or unrooting the standard error. So this is the formula. Now, how are we going to use this? So first of all, is everybody okay with the math? And you don't have to repeat this. I'm not going to ask you to do this calculation. I just want you to show you it comes from the first formula. And the first formula comes from our understanding of making intervals of a normal distribution or a symmetric distribution with the standard deviation. So anyway, everything is related. So, okay, so this is the formula. Let's apply it before we go. We have a few more minutes and then. So this is it here. Let's apply it to the problem I have in the notes. Let's say first though, okay, so P star is either it's P hat from some sample, some previous sample you have, some old study. P star could also just be P, P. I don't know how, but let's say you just knew it, or you've done this so many times. You've researched this topic so many times that you know the true mean. and you just want to do another study, so you want to know the sample size you should get. And if you don't know anything, use P star as 0.5. Okay, those are your three options. 1, 2, and 3. Most of the time, you don't know P star. So let's go to the exercise and do it, and then we're going to go for today. The exercise is on page 6, or is it the bottom of page 5? Okay, so I solve it there. Let me clear this so we do it again. All right, so here's the problem. Suppose that we wish to estimate the proportion of Canadians who actually understand the Constitution of Canada. What is the approximate number of Canadians who need to be sampled so that a 95% confidence interval has a width of 2 percentage points? So a confidence interval's width, the other word for that is margin of error, okay? Margin of error, not completely, but margin of error times 2. Because you have the width, the total width of the interval is 2 margins, right? From the center, the point estimate. Okay, so that means that, what is M? If the width is 2 percentage points? So that's just interpreting the problem. So M is 0.01, 1%. So now taking the formula, we're going to take Z star over M, square it. And is there a P in here? Does anybody tell us P? We don't know P. So we're going to use 0.5. And what is Z star? For 95%, it's 1.96. I showed you that on the T table. You can also derive it, right? From the Z table. It's 1.96. So let's put everything in. 1.96 divided by 0.01. Don't forget to square, times 0.5 times 0.5. This is equal to N. Don't forget to square. What do you get? No problem. I'm almost done, Luis. The answer, make sure you watch back, or maybe I'll review next class. I'll just end, I'll review this question. So the answer is 9604. So which of the options do you pick? Right, so E is your answer for this problem. Okay, E is your answer. What if your options instead were which one did you pick? It's okay, go ahead, Diana. I'll pick up from here next class. Everyone's leaving. Which one would you pick? Very good, Damaris. Yes, you're going to pick the higher one because you have to round up. Even though this is closer, the rule is not about closer when it comes to a sample size estimation. You have to pick the one that's higher to maintain the margin. So I'll pick up from here next class. I'll let you guys go. But yes, it will be, the answer in this case will be still E, even though this one is closer. Okay, so I'll start with this next class. Have a good weekend. Have a good week. Keep going with inference. Bye.
Professor, can I speak with you quickly?
Yeah, sure.
I just want to say this will be the last class that I will be able to attend.
Okay.
That's due to my job schedule. At least I think I completed like 5 sessions that I think
Okay,
that was
good.
minimum.
All
But
right.
yeah, I sent you an email talking about that.
Okay.